Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by SatSearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello everybody and welcome to today's episode of the Space Industry Podcast. I'm joined today by Adrian and Michael, who've actually been on the podcast before, from Texas Instruments. Texas Instruments, a company that's, as I mentioned, I think when they were on the podcast previously, is probably a company that you've heard of. And Texas TI is making some really interesting inroads into the space industry and working on missions in a lot of different aspects through providing advice, support, but primarily in the electronic space. So today, we're going to talk a little bit about some of the trends that TI are seeing, that Michael and Adrian, in the power of space electronics. And obviously, power, a vital aspect of any system, any circuit. Without the power, nothing's going to work. So it'll be really interesting. Obviously, the space environment places some unique restrictions and challenges on how the electronics can be powered efficiently without manual intervention, obviously, because of them being in orbit. And yeah, it'll be really interesting to see what TI is observing in this area, what lessons can be given to engineers, and how this can improve space missions moving forwards. So firstly, let me welcome you both to the podcast. Adrian, Michael, great to have you here.
Yeah, hello. Great to be here again.
Thanks for having us.
Fantastic. So let's get into this topic today. Now, considering the enormous and growing use of electronics in space, I wondered if one of you guys could give a brief introduction to electronics power architectures in space. What do engineers need to be thinking about in this area when designing missions?
Yes, let's take a quick look at the full power ecosystem in a satellite, from the power generation to the storage to the power distribution to the actual point of load. So when you look at the power generation, that's typically done with a solar panel. We're looking at voltages of 100 to 200 volts being generated there. And that needs to be then converted down to the actual battery voltage or battery charge voltage, depending on the state of the battery. We're looking then at maybe 24 volt to 70 volt. Then when you look at the actual distribution of the power, what we see is typically is used a 28 volt bus there. And that 28 volt shall be really stable and shall be independent of the battery voltage. So you need to then either boost it up or use a buck to bring it down. So you're having a buck boost topology for that 28 volt generation. This voltage rail is being submitted to all the different modules and submodules in the satellite. And at those submodules, you then typically generate the voltages you need there, like 12 volt, 5 volt, in some cases also negative 12 volt, negative 5 volt, negative 1. All these voltage rails are then generated typically in a isolated way, having an isolated power supply there for the purpose that if something goes wrong in this module, you don't want to have any faults propagate back to the satellite and eventually bring the entire satellite down. So if there's a fault, you want to isolate it there and keep it also there. And then the last step is then really generating the voltage rails needed for the individual devices and subsystems. Are like for an FPGA, you have the 1.8 volts, the 1.2 volts sometimes, or even down to 0.8 volts. So these are then what we call them the point of load. So all these are, I'd say, typical values, and also how I described this is very typical. There is no standard as of today, but this is coming, right? We will more and more standardize on these things.
Let me also, that's a good introduction, Michael. Let me also add some challenges we see in this area also. Because if you think about power generation, complete system is very expensive, right? So you have huge solar panels, you have all the unfolding mechanisms, so a lot of weight and size involved. And in addition, what Michael also mentioned, if your system is working on the dark side of the Earth, you need to think about batteries, right? Which again adds weight and cost to your system. And also one thing you need to keep in mind is there is no airflow there, right? So you cannot use a fan to cool down your system in space, right? So all the heat must be radiated away, which again adds significant costs and design effort to your cooling system. And last but not least, you're also working in harsh environment. So you have high radiation levels, which are dependent on the orbit you're working. You have extreme temperature cycles, right? If you think about a low flying satellite, those satellites are passing several times per day in orbit and passing from the cool side of the Earth to the hot side of the Earth. So a lot of temperature cycles involved. And also mechanical stress. It's something you need to consider, right? You have all the vibration during the launch of the satellites. So in general, a lot of challenges for designers when thinking about a space power system.
Right, brilliant. Thank you both for the overview. I think that's a really good introduction. Very interesting to discuss the different voltages involved and the lack of standardization, because you think we're talking about systems that are operating in space. The risk of space debris is always there, but the risk to adjacent people is zero, and the risk to adjacent systems and everything nearby is absolutely minimal. And so we could potentially have enormous, huge voltages and currents, but obviously not, because we need to test these things on the ground before launching. We need to launch them safely and effectively. And all of the equipment is built and developed on the ground. So it's very interesting. And also, thanks, Adrian, for explaining some of those challenges. We think of space as being freezing cold, obviously, but still there is no airflow. So yeah, heat must be dissipated through radiation. There's no possibility for convection. So despite the fact that 10 centimeters this way is freezing cold, you still need to remove that heat effectively. And I think both of those things are examples of some of the challenges that players in the new space market need to face, companies that maybe don't have this long heritage of legacy space missions and experience. So power management and also in the new space market, we're typically seeing products and services that are being produced at a lower cost, possibly a smaller form factor, although maybe that's changing in some areas, and on a more rapid timescale as well. So I wondered whether you could touch on some of the reasons why power management is probably more important in the new space market, at least is very crucial in the new space market.
So when we talk new space, I think first we need to probably say, what do we really understand on a new space? It's the way we look at it. It's mainly about private investments, and that means you have a business model that really has to provide a positive return. And so our customers have to balance the risk versus the cost. And many times it's more a compromise than a balancing. And then people do also look into our devices, like we call them commercial off the shelf. So they're not really made for space at all, but still in the absence of a radiation hardened or a cost effective alternative, there's simply no way than using one of those devices. So many times that's true for the high performance processors or FPGAs. So the power tree here plays a pivotal role, as the one thing, it's cost by itself. So the power tree itself is a major cost contributor. It's complex. It's there for every of the modules and subsystems. And this is not less complex than for any large satellites or any traditional mission. You have to provide the full functionality. There is no way to compromise there. Then the protection of the device is downstream, right? So as we said, it's like maybe we need to compromise a little bit on the radiation hardness of the devices downstream on the bus. They might be more exposed to a latch-up situation. And this is where the power tree is your last safety net, your last resort to catch that quickly. And you identify this increase of current quickly and turn off this power tree as fast as you can to rescue those devices, if you will. And then to make things even harder is your power devices are the ones that really carry the current. So, and transistors that carry a heavy amount of current are even more exposed and more at risk to have a gate rupture under any heavy radiation. So this is where we really see that these devices typically really have to be built up, ground up, designed ground up to withstand. So you see that the high dependency on the power tree and the power tree itself being even more at risk, and the cost associated with it really makes it a very pivotal role.
Also to mention, it's also very important to think about the power density, right? And there are several factors involved in that. Obviously, the efficiency of your system, right? Because if your system is efficient, you save twice, right? So if you think about this, you need to produce less energy, and at the same time, you have less energy to cool, right? So you can save costs there. So meaning of power density is really taking advantage of your efficient system and then sizing down the complete solution. So if you think about this, if you're switching at higher frequency, you can, for example, use smaller passive components in your system. So the complete solution size is shrinking, right? And we are focusing at TI on bringing those things to the next level, really. So not only focusing on increasing the efficiency, but really thinking about the complete system and how to increase the power density of the total system here.
Okay, yeah, that makes sense. I think that's a really important message. Thank you. That the higher the efficiency, you can make double savings, because less energy is required to be produced, and then you have to cool it. So that's great. Thank you. So when we're talking about space systems like this, Michael, you mentioned that the complexity for the smaller system is in some ways no less than that for a larger vehicle, because you still need all the different requirements. But there are lots of different ways, I'm assuming, to optimize the electronics architecture, the electronic power system. I wondered if you could touch on some of the most important factors that engineers need to consider when doing this optimization, when trying to achieve these performance levels.
Yeah, that's really good question. And there are several factors here. And one of them obviously is your mission profile, right? So radiation hardness level you need to work with. And there are two factors important: single event effects. Those are dependent on orbit, but also the total ionizing dose, which is also somehow dependent on your orbit. But because those effects are more cumulative effects, it's more important to look at the duration of your mission here. Another factor is, for example, the temperature profile, right? I was already describing it a little bit. If you compare LEO satellite to GEO satellite, obviously the LEO satellite is much worse, because you are passing several times a day from hot zone to the cool zone. And also the material set used in those components is more important, right? Because you need to consider those temperature cycles there. So the designers optimizing power electronics have several options to choose. And the obvious one and the most famous one, let's say, is the QMLV product. So the highest robustness available on the market with highest radiation performance, but at the same time, very expensive and big in size, because those components traditionally use ceramic packages, which are bigger than plastic packages. And if you look at the other extreme, designers can also use commercial components in your systems, right? Because that's also possible. But in general, this is not a good idea. And Michael was already mentioning a little bit, you do not have all the test programs in place for those commercial components. So you cannot make sure they are really withstanding all those radiation requirements. Also, those components, and we see it especially for space power, are not performing very well. This is because the main part of your power product is the transistor. And this is very sensitive to radiation. And that was also the reason for TI why we decided to have a dedicated product line for space power. Because we really need to put design techniques in place to make sure those components are really performing well under radiation. And also, what I was mentioning, the material set used in commercial components is not really made for space. So that's also very important to consider. So there is also a solution in between. We have in our portfolio product space enhanced products. So those are plastic components with radiation performance. So we typically characterize them up to 30 kilorad and 43 eMeV. This is something which designer can decide to use, and it's a very good compromise if you look at the costs versus risk of, and you have all the radiation data available on ti.com, and you can be sure that the material set used in those components is really made for space.
Brilliant. That makes a lot of sense to target that compromise, as you mentioned, that between the cost and the risk of failure. I think particularly for, as we're seeing new space companies and missions maturing into commercial services, the reliability and consistency and lack of risk are so important for these companies as they're professionalizing. And so ensuring that there's a product set, a component set that can meet those needs is very important. And the difficulty with testing anything for space and in space obviously does and should limit some of these components. And when you're talking about, we talk about it at obviously a payload level or an entire satellite level, but at the component level, there's a myriad of variations on each of those components, each of the configurations that all really need to be tested. So approaching it from the materials level as well is very important, I think. And actually, following on from that, when we talk about these companies professionalizing their services and their systems, there's a bit of a movement in the way that some companies are communicating, where we're discussing less about the hardware on board and more about the results that can be achieved, particularly from in the LEO and MEO satellites. It's more about the service that you can provide. And a key part is a similar sort of analogy to nobody cares that much anymore about the hardware in their computer. They want to run the software on it when they're communicating to their end users. Because of that, we've seen a big increase in onboard processing systems and more complex software programs that are being run on satellites. But in order to build them in the first place, they need the right power architecture and control architecture. So what are these uses of more powerful software? What do they mean for power supply? What are they? Is this different from pure FPGA applications? Are you seeing more requirements and challenges by your customers in this area?
Yeah, fully agree with you, first of all, that the onboard processing capabilities will greatly increase in the future and have increased already. There's no doubt on that one. But maybe before we really look in the actual tree, let's look into what is driving this really. And maybe if you look at the example of a communications payloads like we have them in these LEO constellations, one thing you're really looking up there is there is now more need for intelligence and processing capabilities in there, as these satellites are meanwhile not pure transponders anymore. They are really like base stations in the sky. They're doing routing of the traffic through various channels on it. Then you have the antenna technology has greatly moved further. In the past, you had these classic mechanical antenna pointing systems, where today you're using phased array antennas and you use the technology of beamforming and have them electrically steered. That requires a lot of processing in the background to make that really happen. And you have here another driver on top of it, right? Staying in the RF front end, there is, meanwhile, the data converters have increased in speed significantly, right? We're really sampling at multiples of gigahertz, and that generates an enormous amount of data. All that data, of course, has to be processed. It's a good thing because now we can skip the intermediate frequencies and we make the system even more compact, and we call this RF sampling. But now we need to deal with this enormous amount of data, and that needs, of course, decimation and filtering capacities and more processing needs on that end. Then the keyword and buzzword of artificial intelligence, right? So when we look at our communication system, we are taking advantage of our machine learning and artificial intelligence, that we understand what are the best routing opportunities, what's typically the best decision making here to optimize the network loads overall. And yeah, the topic of artificial intelligence is not only going here into the communication payload, but also look at applications like radar imaging or optical imaging payloads. Also here, the resolution's getting better and more data is being generated. But you need to be now smart in compressing this data and selecting the data, pre-processing the data before sending it to Earth, as the bandwidth to Earth is really what's really expensive. And another angle that drives processing, to give a fourth example, is the topic of space debris. So our space vehicles need to be intelligent now in detecting any space debris out there and then make the right maneuver autonomously and avoid any collisions that way. So all this drives the computational power. In terms of hardware, that means for us, our FPGAs getting bigger, and we see already that the FPGAs integrate, meanwhile, multiple cores, right? That is where we see, of course, the software aspects getting more important. In the end of the day, as a designer, yes, you wish you just do the software, but from a hardware perspective, we have to make it work first. And that is where these extreme large FPGAs, of course, come with their own challenges.
Yeah, and what Michael just mentioned, everything means for power, even more power in the future, right? Because especially if you think about those new great space grade FPGA, those require very high current and at the same time at very low voltages. Right. So the core voltage typically 0.8 volt and 10 of amps, even up to 100 of amps. Right. And at the same time, the tolerance for this core voltage is around plus minus 3%, which leaves only a millivolts in tolerance. So efficiency and power density is very important for those high current requirements. And to serve those markets actually with power solutions, you need to think about products with very high current capabilities and high radiation robustness, obviously. But also at the same time, you need to have a solution with very good step response performance, because we see current load steps at those FPGAs up to 30 amps. So your system need to act very fast. And the voltage, as mentioned, is very low, 0.8 volt. And also the power density of the whole system. So you need to really look at those markets to have a ready solution fulfill those requirements.
It's really interesting. Thank you. Thanks both of you. I think there's a lot we can take away from there. As you touched on all the new technologies that can potentially be used in this generation of satellites. And yeah, it's amazing what can be done, but what requires to be powered effectively and in a controlled manner. You think just taking the space situational awareness, the space debris angle, if you're mandating, which is coming, or is it already in some place, different ways, if we're mandating that satellites must be able to maneuver out of the way of an encroaching system, you need the power to be able to sense the system, to act, to maneuver, fire the propulsion or whatever it is, to stop the maneuver, to get back to the orbit you require, to deorbit to the end of life. None of this stuff is revenue generating activity for the service, for the company. They want to stay in their orbit and produce the data that their customers are looking for. Okay, if you crash, you lose revenue, but all of this stuff needs power. And as you mentioned, step response for those loads. These are systems that can be switched on and off. Deploy the antenna, deploy the solar panel, deploy the cameras even. So it's the power. I can see that constructing the power architecture is becoming an increasingly difficult challenge and is requiring companies like TI to solve these problems for your customers, I'm assuming, and develop the components and the materials, which you mentioned as well, are very important in order to solve these issues. Yeah, I guess on that, I wondered if you could discuss a little bit more about the efforts that Texas Instruments is taking to meet these challenges that the new space industry is presenting to you.
Yeah, there's multiple angles we're supporting our customers here. So we do this with a wide product offer where we really support a scalable system with our having all voltage and current levels required. The current levels up to the 18 amps of a single component. You can parallel it and then come up to the more than 100 amps as in some cases might be required. We talked about before, we have these extreme precision requirements and capabilities provided as the 0.8 volt, only 3% tolerance allowed at high levels. But also when we look into RF systems, we need to have them at extreme low noise levels. So we really make sure that the power tree itself is as quiet as possible. Then we have several protection features we put in there, like for overcurrent, overvoltage, undervoltage lockout, over temperature protection. And we make them also somewhat self-contained if needed with their auto retry capabilities, that if something happens or something's not right still, you have a good way to recover from there. And then we've seen different missions have different radiation hardness and quality requirements, or even sometimes very strict cost requirements. And therefore we have several classes here in our quality portfolio. The QMLV RHA, so really the traditional devices in the ceramic package, targeting maybe more the geostationary orbits or deep space missions or human space missions, radiation hardness, 100K rad, 75 MeV. Then we talked about the space-enhanced products or space-enhanced plastic products in the plastic package. Radiation tolerance, we call it then, to 30K rad, 43 MeV. So where we really strike the balance between cost and quality for new space. And then there's something new called QMLP. QMLP is a radiation hard standard like the QMLV RHA, but as the name says, the P is a plastic. It allows for plastic packages. And that is very interesting because now I can really have a pin-compatible QMLV full radiation hardened device, pin-compatible to the space-enhanced product and plastic device that comes at much lower cost. So that is something that our customers will appreciate very, very much, as it enables a single investment into a platform and then adopt it quickly and easily to multiple missions as they come their way. The QMLP is actually something that TI was very active in helping standardizing it. It was ratified only last year in November, and we will bring out the first QMLP devices very shortly, and even more coming still this year. So there's, I think, is something that will make us all in the industry very happy that we have the standard now available. Yeah, so it's also plastic packages overall, right? They make it much easier for us to fan out new products, as the packages are so similar to the industrial versions. So it's very easy then for us to look at a device, see if we can make it radiation hard, but especially for high frequency devices, we have the very same dimensions and mechanics and are much quicker typically in getting the products out at the right performance level.
Yeah, I think, Michael, also the offering really the enhanced functions in our products is also very essential here, especially for the power system. So if you think about something like redundancy, right? In your satellite system, you have redundant systems, right? And those needs to be isolated from each other to avoid fault propagation. And for those functions, we are offering digital isolators. So that's one example here. And in general, what you were already mentioning, the ability to detect a fault, to isolate, and also recovery afterwards is very important. All the integrated functions we have in our power products, like diagnostics, monitoring, protection functions, even simple enable pin is very important, but also current limit pin. So as an example, you can take what I was already mentioning, our load switches, right? We call them also e-fuses. So you can use those devices to switch on and off portion of your system or fully disconnect your system if needed. So those are also important factors when talking about new space.
Right. Yeah, I think overall, right, how do we support our customers in this new space challenges? I think there are several investments we keep making here on a continuous basis. Is one thing, of course, very important: efficiency and power density. Then the optimization of the performance, like in terms of the quality of the voltage rails, like our ripple transients, very much needed for the huge FPGAs, but also like our best noise for RF performance optimizations. All this integration of features to really make sure this whole topic of FDIR, fault detection, isolation, recovery, is properly supported and best possible supported. And what we're also active is in the support of standardization efforts, and last but not least, availability. So we have huge investments in our manufacturing capacities. We make sure that all our high-rel devices are available on our online store. Now, even with all the inventory being visible to our customers, so they know if they click on buy, they will have the device very shortly on their table. And then there is also a strong longevity commitment we give. We call this in our policy, no obsolescence out of convenience. And we know this is an extreme value for our customers, that they know they can rely on these parts for a long time.
Yeah, I think that's great. I think that's very important in the space industry, where we see mission timelines being so long for development and then launch, and then missions get scrubbed, things get delayed by months and months at a time. It's really important, I think, for those companies to know that if refactoring or rebuilding systems are required, that the components they relied on are going to be available. And also, it's great that you're taking a lead in standardization efforts, because I think those are so critical particularly in the new space industry, but in the development of space as a whole. We see these standardization standards being developed on all different sorts of levels and scales. And I think the industry itself is still highly fragmented and very driven by national priorities in some ways, in some aspects of it. Or now we're seeing emerging kind of primary players with commercial priorities that are able to affect big swathes of the industry. And standardization between players is very important. Now, I think following on from that, when we think about the new space industry, where these standards and where these performance levels are emerging, these sorts of companies, new space companies, are often, or have often been, inclined towards launching smaller satellites, or microsatellites at least. Do you think this factor can streamline innovation in power management systems in space?
Yeah, I think absolutely. I think it's important that we're streamlining those things. And the industry is already speaking about standardization. Maybe here as an example, the command and data handling. Here we see NASA helping to make space VPX a sort of standard, or developing something in this direction, or ESA is working as a group called Advanced Data Handling Architecture. And also here we're talking about getting things more modular, more exchangeable, make sure there is redundancy possible with these architectures, that it's easy to switch from one to another. And also the idea of sharing the computational power, as we've seen the computational processing capabilities going up and up, but you may not need all at the same time. So it makes a lot of sense if you can distribute and share those computational power from a hardware perspective. In the end, it's always the same objective, right? You want to get the cost out. You want to increase the volumes, which in fact drives for the economy of scale. And also what you want to do is you want to ensure there's a good reuse of any R&D efforts. So overall, this will reduce the investments from the R&D. And when we talk standardization, that is, of course, what we like to hear from our semiconductor vendor perspective, right? This is what we really like. That makes it really easy for us to make the necessary investments. Right, when we have a clearly defined power supply definition, that enables us to really optimize for cost and performance in the right direction. So we are following all these activities very closely and can't wait until we really have these very clear parameter definitions in terms of the voltage level and current level and ripple and transient behavior. What are the right protection and robustness features people really want to see there? And then in the end, also assure that for this fault detection and reporting capabilities, we support the right recovery strategy in those systems. And yeah, in the end, this is here in space no different than it is already the fact in other industries, automotive, for example, right, where we have a very strong standardization and everybody benefits from it.
Yeah, absolutely. I think everybody understands that aspect of it as well, and it's led to greater collaboration and innovation rather than putting up any barriers in the way. I think this is very important. So it's great, like I say, that you're involved in this area, and it'd be really interesting to obviously share more about TI's work and the work in general of companies involved in the standardization efforts across the industry. So something we're going to look to do on this podcast, definitely. Thank you. And I guess, just finally, just to bring this conversation back to the core topic here, I wondered if I could ask how TI is serving or planning to serve these emerging markets and opportunities in terms of the power control, power management, power architectures, and what sort of plans, what you are happy to share about the plans for rolling out new products for the space industry in the future.
Oh, yes. Yeah. There are really several new products coming, and the number is actually growing each year. So if I only think about 2022, only to give you some examples, I was already talking about the load switches, right? So we released in 2022 our space enhanced plastic version of the load switch, which is the TPS7H2221. If you look at the switching regulators, we released also in plastic package our 18 amps point of load switching regulator TPS7H4003. If you then look on the LDOs, we actually released our first negative LDO in plastic package, which is the TPS7H1210. And finally, if we look at the PWM controller family, we actually released a complete new family of 8 products for different topologies and different mission profiles. Only to give you 2 superset devices. On the plastic package side, on the space and product, we have the superset device TPS7H5005. And on the QMLV side, which is the fully radiation hardened ceramic package device, we have the TPS7H5001. So those are PWM controllers with 2 megahertz switching frequency. So yeah, those are only a few examples, but there is more coming.
Yeah, it's quite a solid product launch cadence just for power in space.
Right. Yeah, and don't stop there, right? This is, of course, at the product level, but each of these products come with their own EVM.
Okay.
And on top of it, we also develop a lot of reference designs and actual use cases. We have our own reference design team called Power Designs Services, or short PDS. So they have developed several designs already, and they're all available on ti.com/reference-designs. And of course, there's more and more coming out of that group that will help our customers to quickly get started on things. And we're also working closely with several third parties and partners, like with our Star Dundee. We're working with them to provide the power for their latest space fiber design, or Teledyne E2V, their latest DDR4 memory, where we provide the power and the termination. And a very strong partner of ours is also Alpha Data. We have developed with them in the past a development tool for the FPGA from Xilinx, the KU60. TI provided here all the core supply and auxiliary supplies and sequencing on it. And moving forward also with Alpha Data, we will bring out the design or the tool for the FPGA called Versal, the latest and greatest and highest processing FPGA for space that Xilinx is bringing or has brought out there. So there again, we will provide the entire power tree for it. And that, of course, customers will then also be able to take advantage of when designing their own boards. So overall, or just to sum this all up, so TI supports this market with a wide portfolio and all kind of products, all kind of quality classes, focus on high robustness, reliability, all the support for the fault detection, isolation and recovery, high power density, and still a high quality of the rails is very important, a strong design support. And then last not least, TI is very much aware of the importance of availability. So we want to make it from our side, make it very easy for our customers to order the devices, and from our side then deliver as fast as possible.
Brilliant. Thank you very much, Michael. I think that's a great place to sum up and to wrap up this. I think, yeah, my thanks to you both. I think this has been a really interesting conversation. I think I've learned a lot, and hopefully our listeners have learned a lot about the importance of the power system in space hardware, and what impact, what is impacting changes in this area and innovation, what the challenges that the unique environment of space presents when you're and how to power all of the systems, the trends in the technologies being used on data processing and deployables, and the requirements for debris collision avoidance, and all sorts of reasons why systems are becoming more power hungry. And then obviously the challenges that this in turn provides, the increases in heat in different areas, the requirements to handle different steps in load. And it's great to also hear about the different levels at which TI is looking to serve this market and solve these problems in terms of optimizing existing components, developing new products for the market, working on the designs and the examples you're providing, and at a high level, working on the standardization and the adoption of these systems. And obviously, yes, availability, as you've summed up, as you were finished on there, Michael, availability and the component level has been a challenge for companies in all different industries over the last few years. This isn't particularly in the semiconductors. This isn't a surprise to anybody. So it's very important that these supplies can be reliably insured for space companies moving forwards, particularly those developing real commercial services. So lots for engineers to take home and to work on this. So yeah, would like to say thank you very much for the...
Thanks.
Thanks so much.
Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.